we go, cool. Hi, slides, please. There, yay, all right, cool. Hi, after all that, I am Alan C. Smith. As Jeremy said, I've been around for a little while, like almost 30 years doing this, which is crazy in our profession. I am Alan C. Smith. I am just ACS on the forums. I'm a consulting software architect, kind of doing my own thing. I've been a certified architect since 2004, which again feels like forever. I'm also a certified embedded developer and instructor. I am a LabVIEW champion, and I am a member of the Actor Framework Guild, which is a new organization of AF enthusiasts who are working on tools and other collaborative efforts to make Actor Framework more accessible to the larger LabVIEW community. But I'm not here to talk about the AF Guild. Casey's going to talk about them, I think, on Thursday. Well, I'm actually here to talk to you about maps and sets. We got maps and sets in 2019, which is 3 years ago. But at the time they came out, I was, of course, working on a project in 2016 and another project in 2017. And so maps and sets came out, and I went, oh, those look cool, but I can't use them yet because I'm in the wrong version of LabVIEW. So they sat for a while. Finally got to projects this year working in later versions of LabVIEW where I have access to maps and sets. And this is not a deep discussion on what maps and sets are and sort of their higher computer science purpose and so on. This is a practical exercise. Oh, come down. Here we go. Come on. Sorry, I don't have the right view on my display. There. This is a practical exercise in just using different components in LabVIEW to solve a problem. And I'm not talking about a deep theoretical one. I'm talking about the kind of thing that might show up in your inbox on a Monday morning. Right? Hey, we have a feature we need to implement, and we need this particular set of data structures behind it to make it work. Go. I got to put this together for one customer. I got to play with a few things I hadn't before. I got to play with maps. Then I got to play with my computer not doing what it's supposed to do. I got to play with sets. I got to play with DVRs, which are not something I use very often. I'm a big fan of data flow. DVRs, can cause you problems. We'll talk a little about that. And of course, it's me. Those of you who know me, this is, of course, a class-based solution, an OO-based solution, so I got to play with classes. And when I pulled all of these things together, I wound up with just a cool thing that I had done. A nice, neat, concise, efficient solution to my Monday morning programming problem. And I was just so taken. I thought it was good, thought it was neat. Some of you may know I'm teaching my daughter LabVIEW. I've put her through Core 1, Core 2, Core 3. And we were working on some practical exercises. We had a whole plan that we were working that night. And I took that plan and I set it aside because I thought this was such a great example of practical problem solving that I thought it was a better demonstration for this new budding developer to walk through the solution. That's sort of the thought process behind it. And that was the genesis for this talk. I actually, shortly thereafter, proposed it to GDevCon. So what was I doing? What kind of thing was I working on? My customer has asked to remain anonymous, which of course I respect, but they build chemical reactors. This is not their stuff. These are images I pulled off of the web, but they're here to just sort of illustrate what we're talking about. We've got an apparatus with some chemical or biotech process going on in it. And of course, we have the control apparatus and HMI that goes along with that. And because this is something that you do in chemical processes, they need to do batch production. We have to have recipes. Okay? And a recipe in our case is really simple. There's just a snippet of one. With some dummy data in it. We might set a control variable to a value and then wait for another control variable to be set. And of course, this is going on in a clean room environment. And we've got the apparatus, and we've got it's Rio attached to it, and we have a little HMI. It's not very big. And our operators are double gloved, and they're using a touch screen. Okay? So one of the things that we had to do was we had to give them away in this environment to very quickly put together a recipe. So we're writing editor, basically a little sequence editor because I'm doomed to continue to write test stand over and over and over and over again, as I think we all are. at some point. But that's okay, right? It pays the bills. So we're laying out this, that was the job. I was asked to give us a way, an HMI with big buttons that they can push to quickly put together some sort of sequence with about 200 process and control variables that they can choose from. That's a mighty long list when you've got a gloved finger to scroll through. And not only do they have their little tiny desktop one, but they've got several, a couple of other larger models of this same thing. They all have slightly different variable lists just because of the way that their R&D has come together over years. And of course, they expect to evolve this over time. So being clever programmers, we're not going to hard code these. We're going to have just some sort of configurable entity that defines the process control variables available to us in our HMIs. It could be a database. We happen to be using a simple JSON file that just lists all of our objects out. So, I wish my screen was closer because I can gesture at it. This is kind of weird back here. So I've got my wait until number in equals 42, where number in is one of my variables, and it appears in my list. Now I've got, as I said, about 200 of these. Think about your poor operator trying to, okay, where is it? Oh, there's the one that I want, right? We need to give them away, given a big bag of variables, to maybe pick, one attribute of the variables and maybe a second attribute of those variables and drill down to the maybe hopefully half a dozen that they care about, okay? So basically we wanted to, we do this all the time in all of our applications, right? We assign tags. I post something in the LabVIEW forums and I get to tag it. That's what they want. They want, I want a list of tags on one side and be able to pick their variables out on the other. Something very much like this, in fact. And I have a demo. It's my only demo. And it's a little one. But I like it. Let me just flip this over where you can see it. All right, there we go. This is not the actual screen. Again, customer anonymity. This is just a demo I put together of some of the back-end code that I wrote, the stuff that we care about for today. So, but it's actually kind of similar to the user experience. On the left, we have the list of all possible tags. On the real system, it's going to be things like temperatures and pH and pressure and mass and et cetera, et cetera, et cetera. And then they can go through and if I fire this up, it is running cool. So it's populated. Here's my list of tags. Here's currently all the variables in my system I've defined, just the dummy ones for the demo. But if I go and say, hey, give me all of the inputs, right? And it'll filter out just my inputs. And then if I say, well, give me all the Booleans as well. And then I get just that one. It might, in a real system, it'll be a half a dozen or whatever, or one actual variable we care about. And then I can grab that one out of my list. And in this case, I'm showing its default value, but I could manipulate it in whatever ways I need to manipulate it. Simple thing, right? Like I said, Monday or Tuesday morning in your inbox programming task for the week. But that's what they want. There's my mouse. So that's what I need to have. My first task is going to be representing the variables in the system, right? Because they have, it's not just a LabVIEW number. There's actually stuff going on behind here, right? Each of my variables has a definition that includes things like the name, okay, or the type of variable. And we support 3 currently. We might support more later. Right now we support 3, Booleans, numerics, and enums, okay? So we specify that type. After that, it gets a little different depending on the variable we're looking at, because obviously a number is not a Boolean, is not the string value of an enum. These are all different things. And then enums are even a bit more complex because in my HMI for the operator, if we pull up an enum, they've got to hit the enum, pull down the list, and pick the one they want. So we have to carry around the list of all the possible enum values as well. So my variables have some structure to them. Now, for those of you who know me, because several of you do, you know where this is going. I sure like me some classes, right? So that's what we did. I declared a base class called step variable. I happened to have 3 children, the Boolean, the enum, and the numeric. which do the specific things of those variable types. And then step variable parent class defines things like how do I serialize to disk or deserialize from disk? What is the snippet of text that goes in the recipe string, right? When we're putting that together, that shows me what the variable is. Okay? Basic representation of data in LabVIEW. Now, going from my file to these objects in my LabVIEW memory, something I've done several times. It is just a JSON file. It could be a database table as well, but in our case, it's JSON. So I go grab my array of JSON objects. For every element, every one of those is a variable. For every one of those elements, I step through and I deserialize the tags, which is just an array of strings. And then I have the block of data that is the variable, and I deserialize that. That is, for any given variable, the first thing I'm going to do is identify type, and then I'm going to go load a default instance of that type because we know ahead of time what ones we're doing. We can preload them into memory, so I don't have to go hunt them down on disk. That's convenient. Once we have the default instance, now I can access the appropriate method to take the rest of the data and turn it into an object in memory. I've done this on several projects at this point. I'll bet if I took a show of hands, a few of you have done, any of you guys done the same kind of thing? Not surprisingly, this is a fairly common thing to do, I think, at this point. One of the reasons we chose JSON is it actually kind of makes it easy for this sort of deserialization. Straightforward stuff. And I have at the end exactly what I want. I have a bag of variables in LabVIEW memory. I have presumably at the same time the list of tags that are available to me for selection. And now we get to the task that I actually want to talk to you about today, which is how I can grab a few of those tags and use them to extract a small handful out of this big bag of variables. So how do I do that? How do I go out finding those variables? Well, let's go back to 2018. We all remember 2018, right? It's good times before everything got stupid. Right? Okay, so here's something that you might do. And this works. This is all valid code. I don't actually have any problem with this. You might decide, I'm going to list out my variables based on tags. Okay? And so I'm going to make an array. Every one of my lists is going to be an array that contains the Boolean, or the variable that goes with that tag, be it Boolean, be it enum, whatever. Right? And then I'm going to take those. I'd love to have a list of those lists. LabVIEW doesn't let you put an array inside of an array, so I have to put it in the cluster first. And then I have that array of lists, which is all of my sets based on tags. I also have to maintain some sort of index. So I'm going to take all my tags and I'm going to put them into an array. And it's not shown here, but then I have to do the extra work of making sure that my list of tags is unique. They don't have duplicate elements. And I've got to make sure that that list of tags happens to line up correctly with the array of lists so the indexing works correctly. I've got a little bit more work to do that I'm showing right here, is my point. But I have to do that, okay? And it works. I can make this go. If I want to go start the process of filtering on a certain set of tags, the first thing I'm going to do is pull out a tag list. That's pretty easy. I go to my list of tags, find that index maps to the array of lists, and I've got my list and I'm good to go. Straightforward stuff. As I mentioned, the array of tags and keeping that synced up does require some extra work. And so for quite some time, we've often done this with a variant attribute table. Who has heard of a variant attribute table? Okay, most of you, who at least knows what a variant is. So anybody doesn't? Well, I won't embarrass you if you don't know. But everybody here knows what a variant is. It's sort of anonymized LabVIEW data, right? I can take any piece of LabVIEW data and turn it into a variant, and then I can handle all of my variants in the same way. Well, variants have a unique feature, which I think cool feature I should say, which I think most of you are familiar with, which is that they can have attributes. I can take a piece of data, turn it into a variant, and then attach it to another variant with a key, with a label. In this case, input. Okay? And the cool thing about that is now LabVIEW does all of that index management for me. which is just awesome. It's so awesome that we've been running around doing this for quite some time and basically eating the cost of conversion, because that's the down check to a variant attribute table, is that I have to convert the data to a variant. And then I have to convert the money to put it in the attribute table. And then I have to convert it from a variant back to my data in order to use it. And that carries a cost. Usually it's a very small cost. Sometimes it's a large cost, but a cost. Performance, memory allocation, that sort of thing. But it works, it solves my indexing problem. Okay, cool. And then so doing my lookup is really easy. At that point, I just go and say, hey, variant, give me your attribute, give me the input attribute, and if I give it a default version of the data, it will give me the actual data back, already converted for me. Yay, good to go. Again, I eat the performance penalty, hopefully small, of converting back to typed data. Either of these is going to work. In either case, once I have that, going back to my problem, once I have here's my set of variables that goes with a tag, I'm going to do that a few times to get the tags that I care about, and then I'm going to have to go get the intersection of all of those sets. Everything that's in set A, I want everything that's in set A and also set B. And then if I have another tag, it's everything that's in that first intersection and also in set C, and so on. And that gives me my list of variables. And I'm done, problem solved. This is good code. I don't have any problem with this. If I came into a project where this is how they were solving the problem, I would not feel any need to change this because it's perfectly functional code, unless I had a performance issue. However, as of 2019, we have a set of dedicated tools for exactly this kind of problem that are incrementally better, and that I would encourage you to pursue and start using. And those tools are maps and sets. So maps and sets, what are they? They are new data types in LabVIEW. They get their own palette, the collections palette, which appears under programming. Okay? And so we'll take a look at both of those in turn. We'll start with looking at maps. A map is a new LabVIEW data type that groups key value pairs in sorted order where all the keys are unique, which sounds an awful lot like what we were doing with the variant attribute table. By the way, the act of putting them in sorted order and having LabVIEW do that work for us, but makes searching faster. One of the things about a variant attribute table is it searches faster than a regular array. And then we preserve that. We still get that in maps with an added and very important benefit, which is that maps can be any data type. The key and the value both. So I can have a map that maps a key string to a value number. I can have my key be a number and map it to a string, which is very, very different from an array in a very important way that I'll mention shortly. I can have a string key go to a waveform, so my data types can be complex. For the ultimate in complexity, I can actually map an object to another object. So in this case, I have a map that is LabVIEW actor framework message class to actor framework incure. Did you all think I wasn't going to say the words actor framework at least once in a presentation of mine? Yes, well that's so I'll actually have an actor framework presentation at GDevConNA in Amsterdam in a month and a half, but that's not here. For our purposes today, we are going to map a string to an array of our step variables, all right? Because that's the map that we want. You don't get a performance penalty for the conversion because this is the native data type. Or these all use native data types. There's no conversion behind the scenes. So we have all the indexing benefits of a variant attribute table. We don't have the conversion penalties. This is a huge win. And then maps come with map functions. These are polymorphic. They work on any map that you define, which saves you time as the developer. Because if I were in 2018 and I did the map that I showed you, but then I wanted to do a map that say involved images, I would have to rewrite all my map code. No, I don't. I have these functions instead. We've got the obvious ones, right? Insert into map, remove from map, look in map, and give me a copy of the data that's at that map location. Okay. They have this in-place map access, which is really handy for being efficient with your data. And so I can go back to what I did in 2018, and I could use a map instead. Okay, I'm still using my array of step variables. I'll tell you what I'm going to do about that in a minute. But the mapping part is, looks a lot like variant attribute table, but it uses a map instead. Okay, pulling data out, getting a copy of. I want one entry of the map out. That's easy. There's a look-in map function. Will give me that. Okay, and the value is still in the map. This is just a copy. I mentioned that in-place element structure, that in-place map access. That's a new border node on the in-place element structure that lets us manipulate the data in the map in place, which is really performant. Here I'm changing the name of one of my step variables in the map, so I don't have to pull it out of the map, incur that copy penalty, make a change, and then overwrite what's in the map. I can just change it in place. Really useful. Deleting a map element, real easy. You do get the map back, get the element back, by the way. I didn't show it here. So that's maps. Now, a pro tip, the map element is a cluster of a key and a value. Take the extra 15 seconds and put a label on the key and put a label on the value so that when you inevitably want to dump your entire map out as an array, you can get the benefit of the unbundle by name function. Otherwise, you have to just use the straight unbundle, which we're all taught not to do for a very good reason. Maps versus arrays. They are different entities. I have an unfortunate habit of, I get a new toy to play with and I push it into places I shouldn't necessarily push it into. And I used a map in a place where I should have used an array. And so I thought, well, what's the articulable difference? So I'm showing two operations here. It's the same operation. I am deleting an element from the data structure. Okay. If I delete the element 1 from my array on the right, when I am done, I still have element 1. I no longer have element 2. So the array re-indexes everything for me. Okay? The map, on the other hand, if I delete the input element from the map, and I go to try to find the input element again, I've deleted it. It's gone. And that's the difference. If you want to re-index every time, use an array. If you don't, if you want that indexed element to be gone, use the map. And there are probably a few others that I haven't quite stumbled into, but that's the general thing. My suggestion, the rule that I'm going to apply for myself is use the data structure that means less work for you. Less replication of code, less fiddly things you have to do. One of the great things about doing the map and set thing that I'm doing here is it eliminates a lot of potential for errors from synchronization bugs between lists of things. So use the one that's going to be less work for you as the developer. All right, let's look now at sets, the other part of this equation. A set is another new LabVIEW data type. It groups unique elements of the same data type in sorted order. So think back to my array of tags. I don't want to just keep dumping tags in there because I'll get the input tag 14 times. That's not cool. If I made a set of tags instead, I could keep putting the input tag into the set, and the set functions are going to say, nope, you already have an input tag. We're not duplicating that. And when you're done, you just have your list. And of course, it's ordered, so search is fast. Like maps, sets are any data type. Okay, so here's a set of strings, or a set of waveforms, or a set of enqueuers, because I got to mention active framework a second time. In our case, of course, we'll just have a set of step variables. We get set functions, just like map functions. They are polymorphic. They work on all of our stuff. So again, that's code we don't have to write. Building up a set, it's real simple. You can imagine sticking this into a for loop instead. I'm just going to add this element to my set. I declare the set type and just add elements to it. Now, pop quiz for the room. I run this code. How many elements are in my set when I'm done? 1. Why? Nope. The set's defined off to the left.
Sorry, I thought it was build set.
No, not build set. That's two. So there's 2 add sets here, but it's going to give you 1 when you're done. And the reason is, even though I have applied a label to each of these default step variable booleans. They are the default values of the objects. They're objects with the default values of the class. And so when you go to add that, I go to add that second boolean into the set function is going to go, no, you already have a boolean with this internal state. So, I'm not going to add a second one for you. So you get one on the outside. Very first time that happened to me, I was like, huh? Oh, well, okay. And it makes perfect sense once you think about it for 12 seconds. So that's going to give you one element back. That's what you want. That gives you two. Okay? Because now I have two Boolean step variables with different names, i.e. different internal states, and so I'll get two elements in my set. Just a little thing to be aware of. It's not going to come up if you're, it's obvious if I were to do, hey, put number 42 into my set of numbers, and I do that twice. Obviously, that's not going to duplicate. Same thing with classes. But for our purposes, so all of that sorting and uniqueness guarantees are really, really handy, and we have lots of ways to use those. The one that we care about for our purpose today, though, is that we get computations on sets. Okay, we get a set of computations that apply to sets working together. And what are those? Well, how about the union of two sets? Give me a set that contains every element in both of my sets that's unique, every unique element in both of my sets. Remember, we did set math. So the very first set math we did was in grade school, and then you do all through school. But that's what this is, right? Give me all the unique elements that are in both sets. Or take all of all of the elements that are in B and take them out of set A. So what I get left is just what was in set A and not in set B. Or give me everything that's in set A or set B, but not both. Or the inverse of that function, which is give me everything that's in set A and set B, an intersection, which is exactly what I need for this problem in front of me. And so I do that. I instead of having my array of arrays, I have a map of sets as my basic data structure. Okay, and I build it up basically. Obviously, the actual code does things with for loops and whatnot, but I've just laid it out here for clarity. I'm adding a Boolean, an enum, and a number to the input set. I add the input set to the map under the key input. Do that for all of my tags, and I'm good to go. I want to search for all of my Boolean inputs. Well, the first thing I'm going to do is I'm going to get the Boolean set and the input set, which is quick and efficient and straightforward. Okay. Actually, we'll back up one because I'm not quite done. Go back. There we go. So, and obviously, if I were looking for a third input, I would take that resulting intersection and I would apply it to the third input. This code is easy to write, easy to read, very efficient, not prone to errors from things like synchronization problems. Okay, so that's the data structure that I'm working with. Let's add some class to this operation, because it's me, and this is what you should do. If I take this data structure, how many of you are using LabVIEW classes routinely? Excellent, excellent. How many of you are doing applications that are basically, it's an OO design? Fewer numbers, not surprising. I assume the rest of you that are using classes are using a few classes here and there. Maybe you've got a hardware abstraction layer. Does that sound about right? Okay. Taking this data structure and wrapping it into a class is an example of something called the aggregation pattern. What the aggregation pattern does is it takes a data structure, like this, and treats it as a single object, the single wire that you pass around through your application. And everywhere that you pass that wire, the class structure, the rules for classes, let me enforce the restrictions on how you can manipulate the data. So this is the actual class I deliver to the customer, and you'll notice that there's a few functions in there, but there's no delete. For example, I don't want my downstream users, my fellow developers, to be able to take a step variable out of the list by accident. That function is not available to them. So I have complete control over how that data is manipulated. That's the purpose of the aggregation pattern. You, as an end user of this API, a fellow developer that needs this feature from me, you only have to worry about this. You don't have to worry about the structure, how it works, any of that stuff. This promotes data integrity. You can't inadvertently change the default value of one of the variables. Right? Why would you do that? I don't want, let's make it so you can't do it by mistake. Hides the implementation from the user. I could have written this in 2008 when we first got classes using arrays or a variant attribute table or something like that. And then I could have converted it to maps and sets, and you, the end user of my class, would never know. This is really powerful for helping us help ourselves to write good code. That makes it really easy to use. I've highlighted 3 functions. The reality is you, the end user of this, are going to use 2. You're going to use create from disk and you're going to use filter. Okay? Really easy to manage this data in this way. All of that adds up to promoting reuse. I will talk about a couple of examples about that in a sec, but let's take a deep dive in the methods first. If I want to create my variable repository from disk, I want to have my access to my bag of 200 searchable variables. That load variable list is the code that I showed you at the beginning about pulling stuff in, off a disk. You've seen that code. Now I have an array that is a variable and the tags that go with that array, those feed right into the add function. The add method looks like this. The action for the moment is on the right. Okay? I'm using the in-place element structure, so hopefully the compiler will be as efficient as it can be. I cleverly named my map of sets. Okay, not my most glorious moment, but there you go. So I take my sets, and for each variable, and then each tag for the variable and each tag for that variable, I loop on the tags, and then I hit the second in-place element structure, where I go looking for that map element. And this enum here, this add or modify entry, that's something that you can do on the in-place map element border node. That if it's set to add or modify, it'll look for my tag. If it finds my tag, it'll return that set to me. If it doesn't find that tag, it will add a new set for me. Okay, and I can set that to other things. So I can make it no, you can only modify, and it'll fail if the tag isn't present. But that gives me back my set. Then I can add my variable to the set, and I can go on with my bad self. Now, I did add one other thing, which you as the end user of my class don't ever actually see. There's a getAll function, getAll method of the class that'll return all of the variables because they sometimes want to see the full list. Instead of filtering on everything, which would be taking an intersection of every single one of my sets, I just went ahead and made a second list, a second set of all of my variables in the all set, which is completely outside the map. And that's just to make that retrieval of all a little bit more efficient. You as the end user never see that underlying implementation. Filtering, trivial. For the tags I want to filter on, it's just an array. Again, loop on all of my sets, search for the sets in question, do the intersection of all of those sets. Don't worry about the for loop on the right. I'll talk about it in a second. Now, I mentioned code reuse, and we tend to think of code reuse as the holy grail of I'm going to have a thing that I can use on 57 projects. That's a beautiful dream. Because reality, where are you going to reuse your code? Well, the first time you're going to reuse your code is when you unit test, right? You all write unit tests, right? Yeah. Not seeing as many nods as I would like. Unit testing is awesome. When you build these sorts of things as a small, discrete entity like a class, it becomes really easy to drop it into a testing framework like VI Tester, like Karaya, what have you, and have a bunch of automated tests that prove that it works. Your testing code is another client of that API, and so that's another reuse instance. And I really recommend that you do this, either test-driven development or testing after the fact. Either way, do tests. Your second reuse instance is not in a different project, but in the same project. Like when your customer says to you, yeah, we think it's really cool that you've given us a variable repository where we can filter out all the inputs or all the outputs. But really honestly, we never have inputs and outputs in the same place. So can you please just give us 2 variable repositories? Yes, I can. That's a straightforward programming test. The other cool thing, and this is why I asked the question about who's using classes and how much, is something like the aggregation pattern is an excellent candidate for use in applications that are not class heavy. I mean, yes, I can use them. I use classes and actors in all of my work all the time. But even if you're not, something like the aggregation pattern, where I have a discrete data structure with some rules, that drops really slickly into more traditional LabVIEW code or into DQMH or what have you, okay? This is the demo that I put together for this presentation, and it is a simple queued message handler. And it's this queued message handler I have been using for over 20 years with a class in it. So if you're not using classes or not using them extensively, I strongly encourage you to look for these kinds of opportunities. Even if you never go with a full-on OO design, your life will get better. This is why we have libraries. This is why you used to talk about making APIs. Okay? All of those benefits, with the class rules to back them up. Now, lecture done. Let's go back to memory management. Let's bring up something that I mentioned right at the beginning, which is the fact that I am duplicating my step variables in my code. I'm making copies of them. If it's a little Boolean like this guy, I'm probably, I think when I flattened one to string, I got 10 minutes? Okay, I'm good. Okay, awesome, thanks. One of these Boolean classes flattens down to about 67 bytes. Not a big deal. The enums could be more extensive. I think I had one clock in at 150 just because I did a bunch of strings. Even that's not a lot of data. For my 200 variables, I might be talking about 20K. That's not a lot, really. But if I were doing this with images, that would be catastrophic. Right? Image files can be huge. So even though I didn't need it for this customer in this application, it made me uncomfortable. I mean, I like to do things. I have gotten a lot of mileage out of doing the right thing always. I call it hygiene. You do good hygiene, and it usually comes back to pay off in the future. So I really didn't want to do this duplication anymore. Now, if I'm back in 2018 again, right, I'm talking about having that master. I'd be leveraging that all set. And I would be having my list of all of my variables, and I would stick them in an array or some other indexing scheme, and what I would duplicate would be that index. And if it's an array, I'm duplicating 4 bytes, and I can duplicate that with impunity. I'll do all the 4-byte copies you want, I don't care. Okay? But that leaves me having to maintain, now I've got the all set, and that's no big deal, but otherwise, usually I'm maintaining this master list. If I delete something, I've got to worry about my index staying correct. I have to do all of that work. It's all that stuff that I didn't want to do before. It would be lovely if LabVIEW had a way to do this for me and just give me a 4-byte number that I can truck around. Like a data value reference. We do have that. LabVIEW does that for us. Who has used data value references? Who has overused data value references and really screwed themselves? So data value references, I'll gloss over this real quick just for the sake of completeness and for the video audience. I'll go ahead and mention it. Data value references are just, I can take any piece of LabVIEW data and I can create a data value reference for it, and now I have a pointer to that data in memory. And if I have that reference, I can access that data and manipulate it. If you have that reference, you can access that data and manipulate it, and we can try to do this at the same time and cause ourselves all kinds of problems, like performance issues and race conditions and deadlocks and so data structure in a by-value language like LabVIEW, references can be dangerous, and they can be incredibly useful. Certain advanced data structures, which can be done in a data flow way, in a by-value way, are much simpler when you use a reference. Also, that reference is a 4-byte number, and if you've got to move a megabyte of data across your LabVIEW application, I would encourage you to stick it in a DVR first and move the number instead of the whole thing, just because you don't want to abuse the memory manager that way. Now, so that's my answer. That's what I'm going to do with my variables to avoid duplicating them. Now, I could just take these functions and drop them right in the variable repository, but go back to what I said about hygiene. Intuition said to me I shouldn't do it that way. Intuition said, no, we don't do things to classes, to objects. We ask the objects to do things to themselves. It's a better way to think about it. So I'm going to ask my step variable to give me a handle to itself. That's the paradigm I'm going to use. okay? And so I added 3 handle methods to the step variable class. Copy, from, delete, and make handle, and they just do the operations here. Copy from uses the in-place element structure and the DVR border node, and you can mark the DVR border node in such a way that says, yes, give me I am making a copy here. I am not manipulating the data in the reference. And that's a little bit more efficient. Once I've done that, I go back to add and filter, and what I'm adding and filtering on is actually the DVRs and not the variables themselves. So the first thing that variable repository does is say, you, step variable, give me a handle. I will put the handle in all the sets that need to go in. When we filter, I will filter and come back with the DVRs, and then we will turn those handles back into variables, which is why we have that check in the code. I mentioned that DVRs can be hazardous. We can protect ourselves. On the class properties inheritance page for classes, you can restrict who can make new DVRs or destroy DVRs of a class. And that's what I did. I said that only step variable can make a reference to itself. And it has to be the parent class. That's the second checkbox. So a Boolean can't make you can't write a function on the Boolean class that makes a DVR. It has to be the one that comes out of step variable. So I've constrained where I can make the variables and the DVRs. And the second thing that I did was I made all of those DVR functions community scoped. Who has used community scope? A few people. Something else I haven't done a whole lot of. Community scope says this method can be called by the owning class and one of hopefully a very short list of friend classes. And so I made variable repository a friend of step variable. And so what I did was I made it so that only step variables could make step variable DVRs, and only the variable repository can ask a step variable to do that, which is pretty secure. That's what I delivered to the customer in the 2019 version of the application. When we hopefully get to go to 2020 or later, I'm going to make this better because interfaces make everything better. That's what we're going to do here. Who's had a chance to use interfaces? Not as, okay, of the people using classes, start looking at interfaces. They really do make everything better. The kind of the principal thing that I'm looking at is, so classes they're defined by 3 things. They're defined by their identity, what they are, what they're supposed to do, their behavior, what we can do with them, and their internal state. Okay? If you look at the step variable functions for handles, they do not touch the internal state, the attributes of the class itself. Okay? They act on the data as a whole, but not its individual elements. Okay? So they don't require state at all. That's an interface. An interface is only identity and only behavior. So we can come back and you'll see why this is, where I'm going with this is when I'm done, I'm going to have a version of the variable repository that I can use in any LabVIEW data type. Any LabVIEW class, I should say. So what I did was I said, hey, let's take those 3, they only touch the class as a whole, and let's put them into an interface called taggable. And then I'm going to say that a step variable is a taggable. It inherits from taggable, which means a step variable can use all of those methods on itself to generate a DVR. And then I go back to that, and I take them out of the step variable class. They don't need to be there. I got 3 minutes to wrap up. Okay, cool. I will make this quick. I'm almost done. That's really cool. Only taggables make DVRs. Step variables are taggables. They can make DVRs themselves. The protections change just a little bit because they're fixed for interfaces. This is the only thing that makes sense. You know, member VIs of the class can make references, but not the interface itself, because that doesn't make any sense. So the final thing that I deliver to the customer looks like this. There's step variable, which happens to be a taggable. So I got the taggable interface, which defines how to make a DVR of something, of anything, of any LabVIEW class. I have the step variable, which is a taggable and therefore can make DVRs of itself, but they're not connected other than that. The taggable repository, every place where I call a step variable in the taggable repository is replaced by a call to the interface instead. And so anything, I can go make classes that are images, for example, and declare them to be taggables, and I can put them into my taggable repository without that horrendous memory issue. And then just to make sure that taggable repository didn't know anything at all about variables, I pulled the create functions out and put them into a separate library. And that's it. That's what I delivered. That was the solution to my Monday morning programming challenge. And I was so tickled with it because I really got to play with all the toys. It's kind of what it felt like. I got to do the things I mentioned, map sets, data value references, and classes. And then I even got to pick up a couple of bonus things. Community access scope. I think it's the first time I've used it. Hasn't come up before. DVR restrictions on classes. First time I got to play with them. And I think it worked out really, really well. And then static dispatch methods for interfaces. This is like the kind of thing you do with those. And that's all I got. Contact me. I'll take questions at this point. You can find me in any of these things. If I don't know you and you go find me on LinkedIn, tell me you saw me here, and I'll make sure to add you. Videos of past presentations go up on Ready on the Wire. I will now take questions. That good, huh? Well, find me later if you have questions. Oh, hey, question, excellent.
All right, we just have time for 1 or 2 questions.
Alan, thanks. I've been using maps for a while.
Yeah?
I've found myself on more than one occasion wanting to make a map of a map. Map of maps. Do you find yourself in similar positions? And if you have you looked a different way? Do you think of other architectures solving that problem if you want to do that?
So, like I said, this is really my first chance to use maps in a serious way. So I don't think I have a good answer to your question. I don't see any reason why you, I think we got an answer right here. I might just pass the mic to, it sounds like you might have. I'm gonna pass the mic to somebody who's maybe done it more than I have.
So I've used them as a sparse 2D implementation as an example, or a 3D implementation. You can nest them however many levels deep you need. But one thing I found much easier is collapse all of those into a single key cluster. And so you still have a single dimensional map, but you get an efficient lookup based on the cluster data. And then you don't have to have the many layers of steps of pulling out and putting back in, and it's just much easier that way.
I do know that variant attribute tables were often nested in the way that you're talking about, because your attributes being variants can also have attributes, and so people would nest them in that fashion. I haven't done that much with them. That's hey, even old guys like me get to try new stuff once in a while. Anything else? All right, I think I'm done. Thanks. Catch me later if you have questions.